Hi there, Connor Makowski here. I work at the MIT Computational and Visual Education Lab, or CAVE Lab for short. One of the questions we often get asked at the CAVE Lab is, how do neural networks work? Well, it turns out, while they might seem complicated, they have some pretty simple roots. And so today we're going to be using a program provided by TensorFlow to help visually understand how neural networks work. In this case, I'm going to start by directing your attention to this right-hand side gray box. In the box, you can see that there are some orange dots and some blue dots. And today, what we're going to try to do is separate the orange dots from the blue dots. Well, it turns out humans are pretty good at this kind of stuff, and we could probably just draw a line from the upper corner to the bottom corner. And in this case, we could say anything below the line is orange, and anything above the line is blue. And that's pretty simple. But what we want to do is train a computer to do that. And so we're going to use a neural network to do that. Neural networks are very good at classification problems. That means separating and predicting a specific object, like something as a cat in a picture, or in this case, an orange dot or a blue dot. More specifically, anything that is really orange we're going to consider -1, and anything that is really blue we're going to consider +1. And so if something is gray, what we're doing is we're actually going to say that that is 0. So in this case, we're predicting right now. We're not using any predictions. We're saying anything in the square we're going to predict is 0. Now we also have an x1 axis, and so this x1 axis is going to run right here along this bottom horizontal. Now we also have an x2 axis, and so that is going to run along this side vertical axis. And so in this case, we could say, hey, look, we've assigned this a coordinate plane. If x1, in this case, if x1 is greater than 0, there's going to be a line here, and we could say anything that's greater than 0, we'll call it a 1. Anything then less than 0, we're going to call it a -1. So anything greater is a blue, anything less than is an orange. So let's go over here and actually show, given x1, we're going to multiply it by some value, and that's given by the weight of this line. In this case, the weight is really close to 0. But what we can do is we can actually update this weight, and we can say, hey, based on how far off I am from being correct on all of these dots in the entire picture, I want to update that weight and try to make that weight the optimal value so I can determine what this relationship is here. And so if I adjust that and I do just one iteration, I say, hey, what's the best way to split this data? On my first iteration, I'm going to check, and I'm going to draw something like this. So in this case, we're going to multiply all the values in x1 by something close to about a half. So that's a positive value. So in this case, let me generate some random ones. If I get one that's negative, in this case, orange means negative again. Remember, orange is always negative. So if I'm multiplying x1 by a negative value, that means blue is going to become orange, and orange is going to become blue. So remember, -1 times -1 is +1. So in this case, you can see that my negative values, or what would normally be considered negative, are now blue. And so you can see by updating the weight of this line, it's what I'm multiplying this value by, more or less. Let's take some of the math away from that. So I'm going to be a little incorrect on that, but the idea is we're multiplying it by that value, and that is going to give us the estimate for what we think is going to happen here. And our goal is to minimize the total amount of error that we have, or how wrong we are. We want to make ourselves the least amount wrong as possible. So let me run this. Let me go again and do a couple steps here. And each step I do, I'm going to try to make that prediction a little better. And so what I can do is I'm just going to make this more and more positive. And as I get more positive, I get real close to that original estimate that I said, remember, if it's greater than 0, I'm going to call it blue, otherwise orange. Now we can do the same thing with our x2. Remember, x2 spans this axis here. So I can randomly generate a multiplier. In this case, I'm negative again, and so remember, being positive means I'm blue. Well, in this case, it's a negative multiplier, so it's orange. So what I can do is I can take some steps, and look, I'm going to learn pretty quick, hey, look, it turns out that's actually a positive relationship, not a negative relationship. So what happens if I want to make a line that's not just left and right or up and down? What if I want to make a diagonal line? In that case, I can actually take both of them together and make a slightly diagonal line. So in this case, let's randomly initialize some different settings. And so you can see we're going to initialize some settings, and then let's do a couple steps. Well, it turns out that remember, as both of them are more positive, they're more blue. As both of them are more negative, they're more orange. And so negative means negative and positive means positive. In this case, you can see that there's a positive relationship for both x1 and x2, and that means we're going to get a line that splits from that top corner to the bottom corner, just like we initially thought. So this isn't too complicated, but what if the data is a little bit more complicated than just drawing here? What if the data is, say, an outer circle of orange around an inner circle of blue? Now, a really smart analyst could look at this and say, hey, I'm pretty smart, and I know that this is a nice coordinate plane that's centered right here in the center of the blue. Maybe I can use squares. Remember x squared and y squared, and there's a lot of circle stuff there. So let's say I take x1 squared and x2 squared, and I use, for example, this x1 axis multiplied by its square, and this x2 axis multiplied by its square, and together I want to train them. And what I can do is I can actually train it and get a circle pretty well. So now what I've done here is I've actually done 160 iterations where I'm learning. So it turns out a negative relationship for x1 squared and x2 squared yields this really nice circle that splits our data. But let's say we have 100 variables and we need to find a relationship. Well, it turns out we can't compare all of them and determine different types of structures. Maybe it makes sense if it's a circle, maybe if it's a triangle it doesn't. How do we find a generalized way of doing that? Well, neural networks offer us a really nice way of doing that. So remember here, we have our x1 and our x2, and together they can make a line. So let's train this. Well, it turns out when I train it, I can't really make a very good line that splits this data. It turns out most of the time, about half the time I'm wrong, because half the time I predict, well, it seems like almost all the time I'm predicting it's going to be orange. So you see the shade of the background predicts the outcome. So in this case, the orange background indicates that all of this area is predicting orange, and down here, all of this area is predicting blue. Well, how can we make this a little bit better? What we can do is we can add an intermediate prediction, and this is called a hidden layer. And so let's add a hidden layer, and let's have a single neuron to it. A neuron is the intermediate value in the layer. And so here we've got our bottom layer, just has x1 and x2. An intermediate layer will actually have different values in here. And then what we're going to do is we can make these values, in this case, we can only make this a straight line, which will make our end goal only a straight line as well. So let's run this real quick, and we can see a straight line forms. But if we add a second neuron, that means not only we have x1 and x2, we also have this intermediate layer, and we have two things. So we can have a combination of two different straight lines that don't just go vertical and parallel, or vertical and horizontal, but any direction. So what happens if we train this? It turns out we can actually form something that's like a U or a V. In this case, you can see here, we've got a line. If I hover over this neuron, I can see the predictions for that neuron. And that neuron is going to predict a line like that. The next neuron is actually going to predict a slightly different line that runs along a different part of the picture. Together, they're actually creating an end outcome that's actually more accurate. And so those will get more and more accurate as we train this algorithm longer, or as we keep going back and saying, hey, where am I off? What's wrong? How do I change it? Where am I off? What's wrong? How do I change it? We loop through that a bunch of times. Eventually, we do pretty good. So let's go back and let's get rid of this real quick. So how can we separate this data? What do we need to contain something inside something else? In this case, the smallest number of sides of an object we have that can contain another object is a triangle. So in this case, remember we had x1 and x2. We had our hidden layer. Two neurons could make a V, so two lines on the edge. So what if I had three? So let me add a third one, and that means I can actually make a triangle. And that triangle might be able to encapsulate this interior that I have here. Now, yep, look here, you can see that this triangle is forming very quickly. And so you can see that instead of having a circle, which might be more of the mathematical way to do it, we can still get a pretty good estimate of what's going on here without fully understanding the math behind it. And that's one of the reasons neural networks is very powerful. Now let's take this back and let's add another layer. And let's actually add this, let's get a little bit more complicated data. So let's take this. So our data now is, in this case, if I'm positive on my x and positive on my x2, so positive x1 and positive x2, or negative and negative, I'm going to say I'm blue, or positive 1. The same thing except for negative 1 on the opposites of those. In this case, how can I form more complex shapes? So I'm going to start training this algorithm. And so you can see here I can only form 3 different lines. But the next thing I can do, and this gets a little bit more complicated, is I can actually form from these 3 lines, I can form a complex shape over here, and then I can form another complex shape. And the combination of those can do a pretty good job separating this data over on the side. And so you can see here now it's actually learning. Let's make this a little bit better, a little bit more neurons, and that means we can capture more relationships. In this case, if I train it, you can see quickly we get something that forms a relatively reasonable way to separate our data. And you can see in about 245 iterations of seeing what makes a good difference, we form these intermediate layers, and each one of them captures a different thing. In this case, you can see we actually have a layer here that captures pretty well. Again, it's negative, but it captures pretty well that end outcome. So again, this data is pretty simple. I think most people could pretty easily do the math to separate this data without a neural network. What if we get something that requires a little bit more sophisticated math, or something that's actually not mathematical at all? This is actually a mathematical shape. So let's take a second, let's try to train an algorithm that can actually learn to differentiate the shape. So let's add a few more layers. And so now we've got a pretty complex algorithm, some different neurons, and we can try to capture some more sophisticated shapes. So what I'm going to do is I'm going to run this. I'm going to let it run for a while, and you can see over here that again, each one of these intermediate shapes is actually training and creating an object. Now for each layer, the next layer can take all of the objects in the layer before and form more complex objects. So you can see here we're actually forming a way that we're separating this data. And so that's how these algorithms learn. Now do keep in mind that neural networks can be very powerful, but they're also restricted to the data that they can see. So they can't generalize beyond what can be seen. So think in the business world. If you have a very fast changing business, they would look at data that's existed in the past, and this might be sales data, and they might say, hey, I want to predict how many shoes are going to sell this year. Well, it turns out if the styles are changing rapidly, that might be very different, and humans might have a better way at predicting what that's going to be than something that has only ever looked at what has happened in the past. Now again, this algorithm is actually taking lots of times to learn this. And so if you want an algorithm to run a business, you might say, hey, I want you to run a business for a year. Well, it might take it 1,000 years to even get this good. Well, if we look at what we've got going on here, I think a 2-year-old, for the most part, could actually probably draw a way to separate these 2 lines better than this algorithm has done, and it's actually learned for a while. And so we're going to let this algorithm keep running for a while, and we'll come back when it's actually got something decent. Alright, so it turns out that we didn't have a sophisticated enough neural network to accurately predict this problem. So what I'm going to do is I'm going to just make this just a little bit bigger, and we're going to let it run for a while again. Now you can see here that the algorithm has done a pretty good job of predicting an end outcome. With that being said, I thank you for your time.